Welcome back to the deep dive. Today we're strapping in for a bit of a ride.
Oh, yeah.
Yeah, think of it as a high-velocity intellectual shortcut. We're diving straight into this fascinating intersection. You've got theoretical physics, abstract algebra, quantum computation. It's all here.
Sounds intense. What's the source?
We've got just one source today, but it's a pretty provocative one. It's a 17-page paper,
Okay.
and it tries to unify 5 concepts that honestly you wouldn't normally expect to see in the same sentence, let alone the same theory. They usually live in completely different parts of the academic universe.
Right. That's often where the interesting stuff happens, isn't it? When the standard approaches aren't working, you kind of have to look in unusual places for those radical insights.
Exactly. So who wrote this paper?
The author is Nieto. It was published back in 2018 in Frontiers in Physics. If you want to look it up, the ARC-Higgs number is 1810.04521. It's filed under general physics, which, tells you something about its scope.
General physics.
Yeah.
Yeah, that sounds about right for something this ambitious.
It's definitely an exercise in, let's say, structural ambition, big picture thinking.
So our mission for this deep dive, just working from the abstract really, is to figure out the core argument. Why is linking these specific 5 concepts, duality, matroids, qubits, twistors, and surreal numbers, why is that such a big deal, such a maybe profound or even risky idea?
Well, the risk is high, but I think the potential reward is seen as equally high, maybe higher. The author isn't just saying, oh, these things are sort of philosophically similar.
Right, it's not just analogy.
Oh, not at all. The claim is much stronger. It's about a deep, demonstrable structural connection. And then, based on that connection, they make this huge conjecture.
Which is?
That this unified structure might actually be the underlying mathematical framework for, well, the holy grail of modern physics, quantum gravity.
Wow. Okay. Let's get right to that core statement then. The central claim from the abstract seems to lay it all out.
It does. It reads, and I'm quoting here, "We show that via the Grassmann-Plücker relations, the various apparent unrelated concepts, such as duality, matroids, qubits, twistors, and surreal numbers, are, in fact, deeply connected."
Okay, pause there. We show that. So it's presented as a demonstration, not just a guess.
Exactly. And via a specific mechanism, the Grassmann-Plücker relations. We'll definitely need to talk about those.
Right. And then the second part.
It continues. Moreover, we conjecture the possibility that these concepts may be considered as underlying mathematical structures in quantum gravity.
Okay, let's really unpack this. Just listing those 5 together, duality, matroids, qubits, twistors, surreal numbers, I mean, it feels like intellectual whiplash.
It really does.
You've got concepts from geometry, combinatorics, quantum computing, theoretical physics, and really fundamental number theory. It's like throwing all that into a blender.
And insisting it makes a single coherent smoothie, as you say.
Yeah. So our job here is to figure out why this specific combination, supposedly unified by this one mathematical tool, is being floated as a serious path towards cracking quantum gravity. That's the big puzzle. All right, so the power move in this abstract is just putting these 5 things side by side. We really need to appreciate the sheer variety of fields we're talking about here to get the scale of what the author is claiming.
Absolutely. The author even calls them apparently unrelated, which is key. Because on the surface, they really are. Some of this stuff is ancient mathematics, some is bleeding-edge quantum tech.
It's that blend that creates the intellectual friction, right?
Precisely. That's where the potential insight lies.
So let's quickly walk through the landscape these concepts come from. Understanding their origins is crucial, I think.
Agreed. Let's start with duality. It's a really fundamental concept, pops up everywhere.
In physics, like wave-particle duality or electric-magnetic duality.
Exactly. Those are great examples. In electromagnetism, Maxwell's equations in a vacuum have this beautiful symmetry between electric and magnetic fields. Swap them, adjust some constants, and the equations look the same. That's a duality.
Okay.
Or in quantum field theory, sometimes a theory that's really complicated at strong interaction strengths becomes equivalent, or dual, to a different theory that's simple at weak interaction strengths, like ADA-CFT correspondence. It's a powerful tool.
And in math.
In math, it's often about mapping objects to other objects or properties to other properties in a way that preserves the essential structure. Like in projective geometry, points can be mapped to lines and lines to points, preserving incidence relations.
So including duality right at the start kind of anchors the whole thing in this idea of deep underlying symmetries or equivalences in how the universe works.
I think that's right. It sets the stage for looking for hidden connections.
Okay, from that broad concept of symmetry, the paper then zooms into something much more specific, Matroids.
Hmm.
This feels like a shift.
It is. Matroids come from combinatorial mathematics, they're abstract structures, and their whole purpose is to formalize the intuitive notion of independence.
Independence-like. Vectors being linearly independent in linear algebra.
Exactly like that. Matroids generalize that idea. They capture the property of linear independence, but they can also describe independence in other contexts, like cycles in graphs or sets of elements in algebra.
So it's the structure of independence itself, abstracted away from any specific example.
Precisely. You can think of a matroid as defining the essential rules of dependence and independence within a set of elements without needing coordinates or a specific geometric setting. It's purely structural.
So why include them here? What's the link to physics or quantum gravity?
Well, the implication is that the connections this paper is exploring are fundamentally structural or combinatorial at their core. Maybe the way quantum information behaves or the way geometry is structured isn't just about continuous fields, but about these underlying discrete rules of dependence.
So, if a matroid defines the rules of dependence, applying that to, say, a quantum system, what does that mean?
It could mean that the possible states or configurations of that system are constrained by these very basic combinatorial axioms. That's a pretty profound idea.
And that leads us right into the next concept, qubits. Now we're talking quantum information, quantum computing. This feels very modern, very physical.
It is. A qubit is the basic unit of quantum information. Unlike a classical bit, which is just 0 or 1, a qubit can be 0, 1, or, crucially, a superposition of both 0 and 1 at the same time.
Represented mathematically as a vector in a complex Hilbert space, right?
Exactly. A two-dimensional complex vector space. The state of a single qubit is a point on the surface of what's called the Bloch sphere.
So connecting qubits back to matroids.
Yeah.
What's the potential link there?
Well, think about that qubit state vector. It's defined by linear combinations, linear dependencies, if the structure of these dependencies is governed by matroid axioms, as we just discussed.
Then the very geometry of quantum information, the structure of the Hilbert space or the Bloch sphere, might have this underlying matroid structure baked in.
That's the implication. It suggests that the rules governing quantum information aren't arbitrary. They might follow these fundamental combinatorial laws of independence. It's a structural constraint on quantum reality itself.
Okay, so we have symmetry, duality, structure, matroids, and information, qubits. What about space-time? That feels missing if we're talking quantum gravity.
And that's where twistors come in. This brings us back to geometry, specifically the work of Roger Penrose.
Right, Penrose. Twistor theory is his attempt to reformulate physics, isn't it?
It is. It's a radical approach. Instead of starting with points in space-time as the fundamental objects, twistor theory starts with, well, twistors. These are objects in a complex projective space, a kind of abstract four-dimensional complex space.
And the idea is that space-time points emerge from the relationships between these twistors.
Loosely speaking, yes. Events in spacetime correspond to certain geometric structures in twistor space. One key feature is that twistor theory naturally incorporates conformal symmetry, the symmetry under scaling and certain transformations. That's important in physics.
And haven't twistors been useful in calculations? Like scattering amplitudes?
Immensely useful, especially in calculating how particles interact in quantum field theories. Certain calculations that are incredibly complex using standard methods become much simpler, almost purely geometric, when reformulated in twistor space. So their inclusion here suggests the proposed unification might operate within this kind of geometric, conformally symmetric framework.
Okay, that covers 4: duality, matroids, qubits, twistors, physics, combinatorics, information, geometry. What's the 5th one? It feels like the real outlier, surreal numbers. Where did that come from?
This takes us deep into pure foundational mathematics. Surreal numbers are, well, the extraordinary. They were discovered or maybe invented by John Horton Conway while he was analyzing games.
Conway, famous mathematician.
Indeed. The surreal number system, often denoted as 8 OLIs, is this incredibly vast ordered field. It contains the familiar real numbers, but it also contains all the ordinal numbers from set theory.
Ordinals, those measure the length of infinite sets, right?
Right, but it doesn't stop there. The surreals also include a whole hierarchy of infinite numbers, bigger than any real number, and perhaps even more strikingly, a hierarchy of infinitesimal numbers, numbers that are positive but smaller than any positive real number.
Whoa. So numbers infinitely large and infinitely small, all living together in one consistent system.
Exactly. It's a number system that extends the reals in a way that handles infinity and infinitesimals with complete algebraic rigor. Its inclusion in this list is frankly, startling.
So let's just step back and look at that list again. Duality symmetry, Matroid structure, Qubits information, Twistors geometry, Surreal numbers infinity and infinitesimals.
When you put it like that, the author really is aiming for the fences, aren't they? They're trying to build a framework that encompasses pretty much every fundamental aspect of reality we can think of. Symmetry, structure, information, space-time, and even the nature of number itself, including infinity.
It's audacious. I mean, the novelty isn't just jamming them together.
Right.
It's this claim that there's a deep underlying connection, a shared structure.
Exactly. And the author had to explicitly say they were apparently unrelated because, well, they are, until someone shows otherwise. This paper is claiming to be that demonstration.
And maybe the inclusion of surreal numbers is the key to the quantum gravity link. Because, quantum gravity has to deal with singularities, with infinities.
That seems like a very strong possibility. If your fundamental structures like Matroids describing dependencies or Twistors describing geometry are going to be truly foundational, they need a numerical underpinning that can handle the extreme situations where current physics breaks down, like singularities.
So instead of trying to get rid of infinities, maybe the idea is to embrace them, to use a number system like the surreals that can actually manage them algebraically.
That could be the core conjecture. That the solution to infinities in physics isn't to somehow cancel them out, but to realize that the mathematical language of reality itself needs to be expanded to include them naturally. Maybe the universe speaks surreal.
It implies that the very fabric of reality might be woven from a mathematical structure that explicitly knows how to handle different levels of infinity. That's a mind-bending thought.
It is. It suggests the unification isn't just across physics disciplines, but across math, information theory, and physics, all potentially dialects of one underlying algebraic language.
Okay, so if the big claim is this profound unity across these 5 disparate areas, the absolute crucial part has to be the how. How are they connected?
Right. It can't just be a philosophical claim. There needs to be a mechanism.
And the abstract gives us one. It says the connection is via the Grassmann-Plücker relations. This sounds like the mathematical engine driving the whole idea.
It absolutely is. If this paper has teeth, it's because of the role these relations play. To really grasp the claim, we need to understand, at least conceptually, what these relations are and why they might be so powerful.
So what are they? Grassmann-Plücker relations? Sounds pretty advanced.
They come from algebraic geometry. Let's start with something called the Grassmannian. Imagine you have an n-dimensional space, like our familiar 3D space, or 4D spacetime.
Okay.
The Grassmannian, written usually as GK, N, is a mathematical space where each point in that space actually represents an entire k-dimensional subspace of the original n-dimensional space.
Hang on. So if we're in, say, 4-dimensional space-time, so N4, and we consider 2-dimensional planes, K2, then G2 and 4-Ds is the space of all possible 2D planes that pass through the origin.
Exactly. It's a geometric space whose points are subspaces. It's a way to parameterize lines, planes, or higher dimensional subspaces.
Okay, I think I follow that. So how do you give coordinates to a point in this space? How do you label a specific plane?
That's where Plücker coordinates come in. For a given k-dimensional subspace, you can define a set of coordinates derived from the basis vectors that span that subspace. Usually, they involve taking determinants of smaller matrices formed from these basis vectors.
Determinants.
Yep.
Okay, so numbers that capture some geometric information about the subspace, like its orientation or volume characteristic.
That's a good way to think about it. They are components of an antisymmetric tensor that encodes the subspace. Now, here's the crucial bit. Not just any random set of numbers can be the Plücker coordinates of a real subspace.
There have to be rules, constraints.
Exactly. The Grassmann-Plücker relations are precisely those rules. They are a specific set of quadratic equations that these Plücker coordinates must satisfy if they are to represent a genuine k-dimensional subspace within the n-dimensional space. They ensure geometric consistency.
So they're like the algebraic laws that govern the geometry of subspaces.
A thick way to put it. And now, here's the connection that seems to be at the heart of Nieto's claim. There's a fundamental result linking these geometric relations to matroids.
Oh, what's the link?
It turns out that a set of vectors can represent the basis of a matroid if and only if their corresponding Plücker coordinates satisfy the Grassmann-Plücker relations.
Wait, say that again. The geometric consistency rules for subspaces are the same as the rules defining the structure of a matroid.
That's the connection. The algebraic constraints ensuring geometric validity are mathematically equivalent to the axioms defining combinatorial independence in a matroid.
That's That's huge.
Yeah.
So if the author claims these relations connect all 5 concepts, does that mean things like Qubit states or twistors, when described geometrically, must automatically obey the structural rules of matroids?
That appears to be the core structural argument. If you can represent the state space of, say, multiple qubits using coordinates in a relevant Grassmannian, which is closely related to projective spaces used in quantum mechanics, and those coordinates must obey the Grassmann-Plücker relations.
Then they automatically inherit the properties of a matroid structure. The way quantum states can be combined or depend on each other is dictated by these fundamental combinatorial rules.
That seems to be the implication. The same logic would presumably apply to twistors, suggesting their geometric structure is also underpinned by Matroid axioms via these relations.
But hold on, is this just a mathematical coincidence? I mean, it's beautiful that the same algebraic structure appears in geometry and combinatorics, but does finding this shared structure automatically mean there's a deep physical connection between, say, a qubit and a twistor? Or is it just elegant math?
That's the million-dollar question, isn't it? The author presents it as a demonstration of shared structure. In theoretical physics, especially when you're pushing boundaries, finding such deep mathematical elegance and unity is often taken as strong evidence, even before direct experimental proof.
The unreasonable effectiveness of mathematics sort of idea.
Exactly. The hope is that the shared structure isn't accidental, but points towards a more fundamental description of reality where these concepts are truly unified. The power of the relations lies in their ability to simplify and constrain. If they constrain the geometry of twistors and the information structure of qubits in the same way, that's a powerful unifying principle.
So these Grassmann-Plücker relations act like a kind of universal translator then, a single set of mathematical rules that can take structures from pure combinatorics, Matroids, and show their equivalent to structures in geometry, twistors, or information theory, Qubits.
That's a great way to phrase it. It suggests that the apparent differences between, say, the state of a quantum system and a geometric object in twistor space might just be differences in interpretation or context, not in their fundamental algebraic nature. At the level described by these relations, they might be isomorphic, structurally identical.
Which feels like a massive simplification, if true. You're bypassing the specific physics equations for a moment and looking at the underlying grammatical rules, the syntax that all these different physical languages seem to share.
Precisely. It grounds the whole enterprise in the rigor of algebraic geometry. It suggests that the most efficient way to understand certain aspects of quantum systems or spacetime might be through the lens of Matroid theory, using these relations as the bridge.
And finding that kind of simplification, that common structural denominator, that's exactly what physicists are hunting for in a theory of everything, right?
Absolutely. So in this context, the Grassmann-Plücker relations aren't just presented as a formula, they're proposed as potentially the blueprint for reality's fundamental algebraic structure.
Okay, so the first part of the paper, according to the abstract, is about demonstrating this structural unity using these relations. But then there's the second part, the huge leap, the grand conjecture.
Right. This is where it moves from pure mathematics and structure to potential physical reality. The conjecture is that this whole unified mathematical framework.
Is the underlying structure needed for quantum gravity?
Exactly. This is where the theoretical physics payoff is supposed to be.
So what does it mean for something to be an underlying mathematical structure for quantum gravity?
Well, think about the central problem of quantum gravity. You need to reconcile general relativity, GR, which describes gravity and the large-scale structure of space-time, with quantum mechanics, QM, which describes matter and energy at the smallest scales.
And they famously don't play well together. GR is continuous, geometric, deterministic. QM is discrete, probabilistic, deals with fields on a fixed background usually, different languages.
Totally different mathematical languages and conceptual frameworks. The idea here is that the reason they don't play well together is that we might be using the wrong underlying mathematical foundation for both. This paper suggests the true foundation is this unified structure linking Matroids, twistors, qubits, etc. via the Grassmann-Plücker relations.
So the common ground isn't found by tweaking GR or QM individually, but by realizing they both emerge from this deeper shared algebraic structure.
That's the essence of the conjecture. It implies that a successful theory of quantum gravity must inherently incorporate elements from all these domains: the combinatorial structure of matroids, the geometric insights of twistors, and crucially, the informational nature of qubits.
That last point seems important. It suggests space-time isn't just a passive stage. but is somehow intrinsically linked to the information it can contain or process.
Very much so. And remember Twistors, they were already a candidate approach to quantum gravity, trying to build space-time from more fundamental geometric objects.
Right.
By showing, or claiming to show, that twistors are structurally linked to matroids and qubits through these relations, Nieto is potentially providing a more rigorous, maybe even axiomatic foundation for twistor theory itself, grounding its geometry in these fundamental combinatorial and informational rules.
So, the conjecture is basically saying, maybe quantum gravity has been so hard because we've been trying to write the book using the wrong alphabet. The real alphabet has to be algebraic, structural, and fundamentally informational. And this brings us back to those infinities. Singularities in GR, the center of black holes, the Big Bang. These are points where the math breaks down, spits out infinities. How does this unified structure, especially with surreal numbers, address that?
This is where the inclusion of surreal numbers seems absolutely critical to the conjecture's ambition. If you're proposing a new fundamental mathematical structure for reality, it has to be able to handle the places where the old structures failed.
And the old structures fail precisely at infinity.
Exactly. General relativity gives infinite density or curvature at singularities. Quantum field theory calculations are often plagued by infinities that need to be removed through complex procedures like renormalization. The presence of surreal numbers in this proposed unified structure suggests a radically different approach.
Don't remove the infinities, handle them.
Handle them algebraically. Surreal numbers provide a framework where different orders of infinity and infinitesimal are well-defined mathematical objects. You can do arithmetic with them. They don't break the system. They are part of the system.
So the idea could be that the geometry of space-time at a singularity isn't actually broken. It's just described by a value, maybe an infinite curvature, that only makes sense within the surreal number system.
That's a very plausible interpretation of the conjecture. Instead of seeing singularities as points where physics ends, perhaps they are points where the necessary mathematical language shifts to something like the surreals, which are naturally equipped to describe such extreme scales. The underlying geometry, Twistors, Matroids, might require the surreals for a complete description.
Wow. So the solution to infinities in physics might be number theory, a more sophisticated number system.
It's a profound suggestion. It implies that the quest for quantum gravity isn't just about finding new physical principles or new equations, but about finding the correct mathematical stage upon which reality plays out. And that stage needs to be built with numbers that can handle the infinite.
It recasts the problem entirely. It's not just about quantizing gravity, but about finding the fundamental algebraic and numerical system that underlies both quantum mechanics and gravity.
Yeah.
So ultimately, the goal of this unification is to provide that common language, a language that naturally speaks geometry, information, structure, symmetry, and infinity.
Yes. It suggests that the universe's fundamental blueprint draws equally from all these areas. The properties of a quantum bit, the geometry of spacetime, the rules of structural dependence, and the nature of infinity itself are all just different facets of the same underlying reality, governed by the algebraic constraints of the Grassmann-Plücker relations operating within, perhaps, the surreal number system.
You have this hierarchy. Maybe the surreal numbers define the ultimate number line for reality. The Grassmann-Plücker relations act as the fundamental grammatical rules or constraints on that line. And Matroids, Twistors, Qubits are the specific words or sentences, the allowable structures that can be formed according to those rules.
That's a nice analogy. It captures the layered nature of the proposal. It's suggesting that quantum gravity might only be possible when we recognize that the physics has to be built on a foundation that includes non-standard number systems capable of handling the infinities and infinitesimals that seem inherent at the boundary between the quantum and the gravitational.
Okay, let's try and summarize this whirlwind deep dive then. We looked at this paper by J. Nieto.
Right, based just on the abstract.
Based on the abstract, yeah. And it makes this incredibly bold claim. It says it demonstrates a deep structural connection between 5 concepts that seem worlds apart: duality, matroids, qubits, twistors, and surreal numbers.
And the mechanism for this connection is identified very specifically: the Grassmann-Plücker relations from algebraic geometry. These relations act as the mathematical glue, revealing a shared underlying structure.
Then, building on that claimed unity, the paper makes a huge conjecture that this unified mathematical framework could actually be the missing piece, the underlying structure needed to finally build a working theory of quantum gravity.
And a key part of that conjecture seems to involve the surreal numbers, potentially offering a way to handle the infinities and singularities that plague current theories by incorporating them into the fundamental number system of reality.
Just to recap the context, paper by Nieto, published 2018 in Frontiers in Physics, a Sieve identifier 1A10.04521, category General Physics. Highly theoretical, foundational, ambitious work.
Absolutely, the kind of work that pushes boundaries. Whether it ultimately proves correct or not, its significance lies in its sheer scope and its willingness to look for answers by connecting radically different fields. It's forcing a conversation about whether the deep structure of reality might be found in the overlap between combinatorics, information theory, geometry, and even the theory of infinite numbers.
It challenges the silos we often put these ideas into. The claim is that beneath the surface, details, whether you're talking about a quantum computer chip or the curvature of space-time near a black hole, the fundamental rules, the algebraic constraints, might be exactly the same, governed by these Grassmann-Plücker relations.
Twins, as you said earlier, governed by the same deep algebra.
So what does this all mean for us, for you listening? Well, if the very fabric of space-time and the nature of quantum information are fundamentally tied together through the mathematics of infinity, like surreal numbers, it really makes you wonder, is the biggest problem in physics actually a problem of using the wrong number system?
Could it be that simple, and yet that profound? If these Grassmann-Plücker relations literally define the constraints of what's possible in reality, then maybe physics is just the process of discovering the consequences of an incredibly elegant mathematical blueprint, a blueprint that already knows how to handle every level of infinity.
So the provocative thought to leave you with is this. If our physical universe is encoded in a mathematical system that explicitly includes infinities and infinitesimals, how should that change our approach to the boundaries of science, to the singularities and the unknowns? Could the answers we seek lie not in new particles, but in the deeper understanding of number itself?
Something to ponder. We encourage you to think about how these abstract mathematical structures could, quite literally, be shaping the cosmos we inhabit.
A truly challenging and fascinating deep dive today. Thanks for exploring these ideas with us.
My pleasure. It's definitely food for thought.
We'll see you next time on The Deep Dive.